Remember that a dummy variable in econometrics is a variable that can only take the value 0 or 1, and we use dummy variables to code information about group belongings. For example, if I have data on individuals and some of them are men, some of them are women, then I may create a dummy variable that takes the value 1 for one of the groups and 0 for the other group. We can then use dummy variables as explanatory variables in our linear regression models, and that will allow us to capture the effect of belonging to various groups. So in this lecture, we will also look at dummy variables, but with the difference that the dummy variable will become the dependent variable in this case. So for a concrete example, let's say that I have data on students and the dependent variable is whether they pass the final exam or not. So students fall into two groups, and I may code, for example, all students that pass the exam, they have a dummy variable which is equal to 1, while students that did not pass the exam, they have a dummy equal to 0. And the purpose here is try to understand which variables affect this y variable. So the first attempt at modeling a dependent variable that is a dummy variable is called the linear probability model. But I should mention at the beginning that this is not the only way of modeling a dummy dependent variable. We will look at other methods such as logit and probit models later on. So let's get started with the linear probability model. So the setup is as follows. The important part is that I have a random sample where my dependent y variable is a dummy variable. I also have explanatory variables, and it's perfectly allowed to some of these to be dummy variables as themselves. For the linear probability model, I specify just a linear regression model, and I specify it the way we have done many times before, just like this. So my y variable depends on my x variables and an error term. The difference now is that my y variable can only take value 0 or 1. Let's assume that the explanatory variables are exogenous in this linear regression model. Remember, if the explanatory variables are exogenous, then the expression between the equal sign and the error term will be the conditional expectation of y given x. So if they are exogenous, then the conditional expectation of y given x is this linear expression. So with our example, where y is 1 if the student I passes the exam and 0 otherwise, and the x variables could be variables such as the number of hours that the students have studied and so on. This expression is the expected value of y given these x variables. Now, one of the important properties of a model where the dependent variable is a dummy variable is the following. It turns out that we can actually write the conditional expectation as a conditional probability in this case. So let's see how that is done. So let's consider a generic observation, skipping the I index. Then for a dummy variable, we know that the dummy variable can only take the value 0 or 1. We also know that the expected value of a random variable that can take two values 0 and 1 is 1 times the probability that it will take the value 1 plus 0 times the probability that it will take the value 0. This follows from this generic formula for the expected value of a discrete random variable. The expected value is the sum of xi times f of xi. In this case, the second term disappears because of the 0 times, And we see that the expected value of a dummy variable is exactly equal to the probability that it's equal to 1. That's of key importance to these models. This result for unconditional expectations will apply to the conditional expectation as well. So if I look at the expected value of y given x, that will also be equal to the probability that y is equal to 1 given x. For example, if a given student has a 72% probability of passing this exam, given the x variables related to that student, that is, suppose that the right hand side is 0.72, then the expected value of y is 0.72 as well. Now this is important because we can express the exogeneity assumption slightly differently now. We can state the exogeneity assumption as the probability that the student passes the exam given all the x variables is equal to this linear function of the explanatory variables. This only works if you have a dummy variable as your dependent variable, because it's only in that case that the expected value of y is the same as the probability that y is equal to 1. So as you can see, we have now specified that the probability is a linear function in the x's, and that's the reason it's called the linear probability model. So if you have a linear regression model and your dependent variable is a dummy variable, then you can call it a linear probability model. So the next part, remember that we interpret in general in the linear regression model, we interpret the beta parameters as the change in the expected value of y when x changes 1 unit. Well, in this case, the expected value is the probability that y is equal to 1. So we have a different or an alternative interpretation in the linear probability models. So beta 1, which is generally interpreted as the expected value of y when all the x variables are 0, will now be the probability that y is equal to 1 when all the x variables are 0. For all the other beta parameters, the slope parameters, they are now interpreted as the change in the probability that y is equal to 1 when x changes by 1 unit. The old interpretation that beta j is the change in the expected value of y when x changes by 1 unit still applies. But typically this is a much more useful interpretation, as we will see in a short while when we do some examples. So next, let's look at the fitted values. Remember that the fitted values are always determined like this. There's no change, that's the fitted value. We remove the error term, replaces the betas with the estimated b's, that will give us the fitted values. The fitted values are generally interpreted as the expected value of y given the x variables, the estimated expected value. So in this case, these will be estimates of the probabilities that y is equal to 1, as well as the estimate of the expected value that y is equal to 1. So that's very useful. We can do, for example, out of sample predictions from such a model, and the predictions will then be a probability. So if I have a student which hasn't done the exam, I can predict the probability that this student will pass the exam given the explanatory variables for that student. So on to the next question then, and that is, how do we estimate these beta parameters? Well, the fact is that if the explanatory variables are exogenous, as we have assumed, then you can actually do OLS and get consistent and unbiased estimates of the parameters. Remember, the only thing we need for consistent and unbiased estimates is the exogeneity assumption. There is no requirement that the y variable should not be a dummy variable, for example. You can show that in a linear probability model, the error term must be heteroscedastic. It's actually not possible for them to be homoscedastic, so because of that, we should use robust standard errors if we do a linear probability model. However, it turns out that the linear probability model with the OLS estimates, it does have some problems, and we are going to look at that now. So let's have a look at the problems with the linear probability model and the estimates that we get from OLS. So here is the first problem. In the linear probability model, we specify that the probability that y will take the value 1 conditionally on the x variable is a linear function of the x variables. Now, linear functions are always unbounded upwards and downwards. So we can always find an x value large enough or small enough such that this probability is outside the 0-1 bound. So this is a major problem because we have actually allowed in our assumption the probabilities to lie outside the 0-1 bound. So in a very specific sense, the linear probability model is somewhat nonsensical because there is no restrictions for the probabilities to be bounded by 0-1. Now that's a problem in our assumption, and we could probably live with that if it didn't create problems in our results, but it will. Because when we actually do this analysis and we estimate these probabilities, then they will also not be restricted to 0-1. To take a concrete example, I may actually predict that the probability that student I will pass the exam, given the x variables, is 130%, for example. Or I may predict that the probability that another student will pass the exam is negative 20%. And this is, of course, a problem. The common solution in this case is to say that whenever these estimated probabilities are greater than 1, then they are just set to 1. So instead of saying 130% probability, we say that it is 100% probability, which is also a little bit problematic because the probability will never be 100% for no student. And similarly, if probabilities goes below 0, it's common to set them to 0. Now here's another problem with the linear probability model, which is a little bit more subtle. Remember that when we have a linear model, a linear regression model, which is also linear in data, then the marginal effects must be constant. An increase in the value of x will increase the expected value of y with the same amount no matter where you start from. Now this is typically completely unrealistic if the dependent variable is a dummy variable. If you think about the example of students passing or failing the exam, then a constant marginal effect would be the same as saying that one additional hour of studies will increase the probability of passing the exam by the same amount no matter how much you have studied. And that is unrealistic. For example, in a course where students are expected to study, let's say, 120 hours, a student that has studied 100 hours and decides to study an additional hour will most likely increase the probability of passing the exam more than a student that have studied, say, 300 hours and increases that by 1 hour. The students that have done already 300 hours, way above what's expected, then one additional hour will make a very small contribution to the probability of passing the exam, because this probability is already very, very high, and there is an upper limit of 100%. So this might be the most important problem with the linear probability model. That is, it assumes constant marginal effects. It's assumed that the change in the probability of passing the exam is constant and it doesn't depend on the x variable. Now, what must happen is that this probability must eventually decrease as the x variable becomes large. And it's clear because if it doesn't decrease, then eventually by just keep on increasing the x variable, the probability would go over 1. So to summarize the whole thing, if I have a dependent variable that's a dummy variable, and I have explanatory variables, then I can still estimate the parameters consistently using OLS. I will have heteroskedasticity, but I can take care of that by using robust standard errors. However, the implicit assumptions behind making a linear regression model is highly questionable if the y variable is a dependent variable. The linear regression model doesn't recognize the fact that probabilities must be between 0 and 1, and it forces marginal effects to be constant. Now, it turns out that if you want to know the marginal effect for an average individual, average in the sense of the values of the x variables, then the OLS will work pretty good. If I want to know the marginal effect of an additional hour of study for a student that studies approximately the average amount of hours, then the OLS estimator will provide me with a pretty good estimate. However, if I want to know the marginal effect of students in the tails, either students that study very little or very much, then the OLS estimator will not provide me with a good estimate, as it's simply assuming that all students have the same marginal effect. For this reason, the linear probability model is not used that much. It's used in certain situations. For example, when we have endogenous explanatory variables and instruments. But if the explanatory variables are exogenous, then it's typically more useful to use a binary choice model, for example, logit and probit, and that's the topic of the next lecture. So let's look at some actual data and the linear probability model. Here I have some data, 100 students. I know how many hours that they've studied for the exam, and I also know whether they passed or failed the exam. So 1 means that they passed the exam and 0 means that they failed it. Obviously, the number of hours is not the only variable that affects whether you pass or fail the exam. So you can have cases like this where the first student studied 129 hours and failed, and the second student studied only 50 hours and passed. But we would at least expect some general relationship in the sense that the more hours spent studying for the course, the higher the probability of passing the exam. I have made here a scatter plot of the data. On the x-axis, I have the number of hours that the student spent studying, and on the y-axis, I have the dependent variable, which is 1 again if they passed and 0 if they failed. I think in this data, approximately 70% passed. As you can see, it doesn't look like what we normally have when we do a scatter plot of our data. There is no clear trend line in this case, where some observations are above and some are below. But even though there is no trend line, that doesn't mean that we cannot do OLS. We can, and let's just do that here. We add a trend line, and let's put the equation on the chart, and then it looks like this. So it does have a clear upward sloping, we do have an upward sloping trend line, indicating that the higher the x is, the higher the probability of passing the exam. If we look at particularly the OLS estimates, so I do a linear regression. My dependent variable is the dummy variable, and my x variable is the number of hours that we study. We include an intercept and no statistics in this case. We have the following result. So first of all, the interpretation. This one, the intercept, that would be the probability of passing the exam given that x is equal to 0. So in this exam, you actually have, according to this model, a 40% probability of passing the exam, even though you haven't studied at all. B2 is the change in the probability of passing the exam with an additional 1 hour of studies. So let's multiply that by 100 to get it into percent. So we see that 1 more hour increases the probability of passing the exam by about 0.17%. Spend, let's say, a Sunday studying 10 hours, and you increase the probability of passing the exam by almost 2%. Let's do the fitted values, y hat. The fitted values are calculated just like before. The intercept $5 plus $5 times the x value, and the x value is in A2. I copy this down, and these should be interpreted now as the probability of passing the exam. So this first student studied 127 hours. The probability that this student should pass the exam is 64%. Although it turned out that its student actually failed. This student had about 50% probability, and so on. And we can see the problem here that, for example, this student that studied a whole lot, 419 hours. According to our model, the probability that these students will pass the exam is 113%. That's slightly problematic. Even worse with this guy on line 16. In this case, there are no students with a negative probability, but that can happen certainly. So let me also point out again the other problem with the linear probability model, and that is this marginal effect, which is then the same for all observations. So according to this model, each and every student can increase the probability of passing the exam by about 0.17% with an additional hour of studies. So this student, which has studied 17 hours, 1 hour of additional studies will increase the probability of passing the exam by the same amount as this student, which has already studied 501 hours. That just doesn't make sense. There is certainly a decreasing marginal utility of studying for an exam. You can probably still increase the probability of passing the exam if you've studied a lot, but not as much as you can if you have studied a little. Here is another example, and I've now used Gretel instead. I have data again. This is again if student passes the course or not, but here I have more explanatory variables. So I have the result of the SAT math score and the SAT verbal plus the GPA, high school GPA. And if I want to do a linear regression model, it's very straightforward. All I do is just do ordinary least squares. I'll put the pass as my dependent variable, and I include all the explanatory variables just like before, like this. Okay. But then I have to be careful with the interpretation. So here we can see some really weird things. This actually tells us that the student with the 0 on the SATV, 0 on the SATM, and 0 as the GPA will have a minus 264% probability of passing the exam. That is clearly nonsense. And one of the reasons that we get such a weird result is that we have no students which is even close to having zeros for the explanatory variables. The interpretation of the parameters are, again, as marginal effects on probabilities. So this means that one more point on the SATM will increase the probability of passing the exam by about 0.26%, with a similar interpretation of the other parameters.